Okay, good afternoon, guys. This lecture is being recorded. Right, so today we're going to cover the example from the book on page, but it's in 3 parts, right? 6.1, 6.2, 6.3, right? So the first part is the slenderness calculation on page 6.8. So 6.8, let's get to that first, right? So we have this example. 500 by 220, the beams and slabs are 150 millimeters thick. The story height measured from floor to floor is 4.5 meters. The structure is braced about the y-axis only, right? So you've got bracing in this direction. Where should I show it? Let me show it here like this. Sorry. Braced. Now it could be from some bracing system. Could be from a shear wall, whatever else, but it's braced there, right? So about the y-axis. Okay. About the x-axis is unbraced. There's no bracing, right? The story height 4 to 4.5 top to bottom. Beams are 500 by 200, so 220 there and 500 the depth. 150 millimeter thick slab. You got the dimensions of the column is 220 and 350. And you've got a bending moment in the x direction, 64 and 55. This is double curvature. Okay, so this one is double curvature. You've got moment in that direction and moment. So this is a free body diagram that I've drawn on the left hand side. Okay, and I'm taking the moments from the moment diagram and transferring it to the free body diagram. And then I've got here moments about single curvature actually. All right, both moments are not causing, either moment's not causing a point of contraflexure. Here it is, so there's a point of contraflexure. Okay, so you want to look at it, you can look at it like this in terms of buckling. All right, so there's a point of contraflexure. So there we have it. All right, whereas this one, when you bend it, it's just going to do that. Okay, fixed or pinned or whatever. I'm not too worried about the thing, but just understand the principle. So that's single curvature, right? Okay, so I've got the two there in one. So let's see what happens. I'll start with the x-axis. So what do I need to know about the x-axis? Looking at the picture, I've got, that's my x-axis. This is 350. My width is 230. Right? So this is my H. This is my B. Right? That's for the x-axis. When it comes to the y-axis, all right, when it comes to the y-axis, then I'm looking at that y. Okay, so this now becomes my B, and it's equal to 350, and the depth here will be 220. That'll be 8. So you see how we swap it around? Okay, for the different axes. Let's continue. So we start restraint at the top is equal to 1, restraint at the bottom is equal to 1, x-axis. It's unbraced, okay? And we take it as 1 top, 1 bottom, because x-axis affected by, see the direction of the x-axis, it is perpendicular to that beam and that beam. Okay, so those beams are 500. So if you put a reason for it, you will say beam 500 is greater than 300 and where is it? 350. Right, so the depth of the column, right, is greater than the depth of the depth of the beam is greater than the depth of the column, of course, taking into consideration the appropriate axis. Sorry. Just trying to unhook this thing from here. Right, it's better. Okay, so now I've got restraint condition at the top is 1, restraint condition at the bottom is 1 because there's a beam at the top perpendicular to the x-axis, which is greater than the depth of the column. And same thing at the bottom, the beam is the same dimension. Okay, then I go on to, right, so that gives me to the table 1, 1. So I go for 1 here and 1 there. Remember, I'm using unbraced. So it is unbraced, sorry. Oops. So this is unbraced, and that must be unbraced. Condition at the top is 1, 1. Okay, gives me 1.2, right? What is my LO? Back to my sketch. I want the clear distance under the beam to the top of the floor. So it's this height here, all right, which is going to be 4 meter 500 minus this depth of 500. That's 500. So that gives me 4,000 clear LO. Okay, so I've got LO there. Going back. So I've got 1.2 times 4, 4,800. Okay. Short limit for braced, for unbraced is 10. All right. Where do I get that from? Page reference. Where do I get that from? Which page? In the book. Sorry. Some things you have to make references. Okay. So if you go to the book on page 6.7. So let's refer to the book here so it's easy for you and you can write it in next to the example. Page 6.7, code reference 4714. Short limit is 10. You can see there's a top part there in the book, page 6.7. A column is unbraced. So what I would do if I were you, the top part talks about unbraced, right? And then there's the paragraph ends and then there's braced. So put a line here in pencil or something and highlight the 10. So unbraced, you're talking about 10, and braced 17 minus 7 M1 divided by M2. So this is for the braced one. Are you with me? So just do something like that, because when a lot of you are noticing the tests are studying the book. Not supposed to be done there. You just need to find it quickly, know what you're doing. All right, when you don't know what you're doing, then you're sitting. I saw one student, he's got one finger in the equation in the book, one finger here is writing, and he every 5 seconds is turning his head between the book and the thing. That means, told me already what he's going to get. Okay. All right, anyway, so that's just a recommendation. Open book exam is a tricky one, because if you don't know what you're doing, you can have all the books in the world, it's not going to help you. Okay, slenderness ratio LEX over H is 4,800 divided by 350. As we said, H is a dimension perpendicular to the x-axis, right? 13.71 is greater than 10, therefore it is slender. Beta A is the next thing that I need to know, and this comes from table 20. So we're looking for, okay, so let's finish. I'll come back to this. Let's just finish the slenderness ratios, because that was example. Where are we? That was example 6.1, right? So 13.7. So this is where the example in the book on page 6.8 ends. It stops here. Okay, doesn't go any further. And then you look at, jump onto the next one. You want the minor axis, YY. It is braced. So this is now page 6.9 in the book. And this one was up to that point 6.8. Okay, all right, so we're skipping the additional moments, etc., and we're jumping into minor axis braced. Restraint condition at the 2 is top. Why? Because the slab is the only thing you've got there, and the slab is 150 thick, right? And the column dimension, so you looked at the column dimension, you're looking at that axis, and that dimension is 220. So column is greater than slab. There's no beam there, right? There's no beam in that direction, perpendicular direction. You only got the slab. So 150 is less than 220, right? Or 220 is greater than 150. So it's end condition 2. Where do we get that from? Table 18, page number. Page number 6.4. Okay. So unbraced or braced, we've got braced, table 18. We've got the conditions given on page, where are we? It's given on page 6.3, the page before that. Column dimension exceeds beam or slab depth. So that's what we got. End condition 2 at the top. And at the bottom, I've got 1 because I got a nice fat beam or something there at the bottom. Okay. So I've got all beams of 500 by 200. It's not drawn very nicely, but I mean, it's 500 deep at the bottom. So it's fine in that direction. Okay. The beam is greater than the column in the perpendicular direction. So it's condition 1 right at the bottom. So bottom, top sorted out. I've got end condition at the bottom is 1. End condition at the top is 2. So I've got 0.8. 0.8 times the clear distance is, for it is 150 from 4.5. Sorry. So it's going to be that dimension that I'm looking for, which is 4,500 minus 150, which is 4350. And then I'm multiplying that by 0.8. So I get 3480. Okay. The limit M1 and M2 I have to look at now. What is M1 and what is M2? Yes. Listening.
I want to ask that slab, the top part, is it spinning in one-way direction?
Maybe, we're not sure, but the only thing we know is there's no beam there.
But because when I look at the bottom one, it is spinning in two-way direction, so I'm a little bit confused.
No, just from the column, it looks like it's two-way, but it may
Yes.
be. But it may be that there's a beam somewhere else in the slab which we can't see, further back, further away. So we don't want to make assumptions about the slab span right now, because we don't have the full picture. If we had the full picture, then we know. We don't have the full picture. So without the picture, we can only go by what is given to us in the section. There's only 150 slab or whatever it was there. All right. We're not concerning ourselves right now with the span of the slab.
All right.
Okay. All right. So then we look at the limits. We're coming back to that. Sorry, 17 M1 minus M2. Now I want you to go to which page for the moments. Please turn backwards to right on page 6.7. So page 6.7, the formula is there. Sorry, not for that one, for the one at the bottom. So page, just annotate your book so whenever you're referring to it, you know where it came from. Okay, 17 minus 7M1 over M2. Now what's the sign? Because I've got my bending moment diagram for YY axis. For YY axis is single curvature. I was not interested in the X axis, right? Because there was no M1 and M2 in the slenderness thing. The slenderness just said 10 without knowing what's going on in the moments, right? But here I have 10 and what have we got there? 10 and 7. So I've got 10 and 7. Okay, now smaller initial moment, which should be taken as negative for a column bent in double curvature. So this is single. That's why you have to know what this is. This is single curvature. Why is it single curvature? Say it's bending it like that. Take your ruler in your hand and bend it from both sides in opposite directions. Okay, let's see. I can show it to you quickly. Done in analysis, but anyway. Let's see if I can camera. Okay, all right, so there it is, turning in one direction. Can you see? Turning it in the same direction, you get double curvature. If I rotate it in the same direction, double curvature. I rotate it in opposite directions, single curvature. Okay. All right, so that's that one. All right, so single curvature. So what happens when it's in single curvature? You retain both signs as positive. So it'll be 7/10. So both signs here are positive. So just to emphasize the point. So if we're dealing with one like that, okay, we're not, because it's short in that axis. I mean, sorry, it's unbraced in that direction, so we're not interested. But if we had those moments, which are 64 and 55, okay. So this one would be taken as negative. Are you with me? So then I would have had 17 minus 7 times minus 55 divided by 64. I'm just showing you an example. It's not related to this, right? Because mine is unbraced, so therefore it's just got 10. So what will this give me? Calculator, sorry. 55 divided by 64, and it changes the sign, times 7 becomes 6 plus 17. The slenderness would have gone to 23. So if you had less than 23, it would be short. If you had more than 23, it would be slender. If we had a braced axis about the X, we don't, right? But I'm just showing you how the sign works there. Okay, so I don't want to confuse issues. Let me take this out. All right, so let's take that out. Doesn't apply to this example because, as I said about the XX, it is unbraced. All right, so this one, I've got 17 minus 7 times M1 is positive 7 and 10. Okay, so I got 17 minus, what is that? So it's 49, 4.9, right? Which is going to give me 12.1. Right, so there it is. There's the calculation for that. 17 minus 4.9, and 4.9 comes from 7 times 7/10, negative, because it's single curvature. Okay, so it becomes smaller. Double curvature, it becomes bigger. Slenderness ratio, LEY/H, 3480 divided by 220, 15. So you've got to be very, very careful. Right, so you've got to start your problem by identifying which is your X, that's your Y, what's the column in that direction, what's the column in that direction. This one applies to the X, that one applies to the Y. Okay, so you got to figure out all of that before you start so you don't get confused. Right, when you just look at an example like what a lot of students do is they don't study, they don't do a tutorial, they don't do anything. Just look at the book and expect to solve the problem. You're not going to get examples like the book. All right, beta A, 15.82 squared. We'll come back to this now. This is in the next example. So we completed. What we want to know here is 15.82, therefore it is slender. That's the important thing. It's slender in the YY axis and it is slender in the XX axis as well. Although one is unbraced, the other one is braced. Bottom line, it's slender in both directions. Okay, so that's example 6.1. We jump now to the design aspect. So let's look at the design requirements for columns. So I'll jump back into Greg's PowerPoint presentation that he had. for each axis, get the clear height, obtain the effective B, calculate the slenderness ratio. Is the axis short or slender? Calculate an additional moment. All right. What is the additional moment? The additional moment is due to the buckling in the column. All right. So because it buckles, your load is now multiplied by this eccentricity. So this is an eccentricity. This is an eccentricity. So this is your eccentricity. So load n times eccentricity is going to give us a moment. All right, you did this with Mr. Kuzuayo mechanics, right? Moment, additional moment. So that force times distance gives us a bending moment. Theoretically, it looks like this has just got an axial force, okay? But because that axial force now acts out here, so the member's deflected to that position. Let's say it's 5 millimeters away. So the load is now acting 5 millimeters in the middle out of the neutral axis, its original axis. OK, so it creates this bending moment. All right, then the next thing we have to do is slenderness ratio is given to us. AU, we know, is equal to beta A. So how much is that deflection? It can vary depending on a number of factors. So what the code has done is it simplified it to beta A K times H. You can go into detail, and I suppose this will come into your honors program about that buckling mode and how we arrive at those AU values. It's quite a detailed mathematical calculation. It involves integration to higher orders. I did it a long time ago, so I'm not going to go through it right now, but it is a long calculation with many assumptions, and then you try and iterate till you get to what it should be. Okay, so for us, the code has made it very simple. It said slenderness ratio squared divided by 2000. K is another one. This is not the K that we used to from other places, right? Please. This K is now NUZ. So it comes from here. So this is not the K M upon FCU BD squared. Please, let's be absolutely clear about that. This is a different K. What is it? NUZ over N. Okay. And NUZ over N, sorry, NUZ minus N, NUZ minus N balance. So now you need to know what is NUZ, what is N, what is N balanced. You need to know all of these things. Okay, right. So NUZ is given on page 611, right? Please look at page 611. So it's lower down here, so let me show it to you here. Right, NUZ is 0.45, FCU AC 0.75, FY AC, and it's ringed it because generally we don't know the steel when we're starting, so we have to make some assumptions. If it's fine, if we're given a concrete section with the steel, then it's different. But if we're not, the example we did yesterday, we knew the area of the steel, that's how we could calculate it. All right, so this is NUZ. In other words, this is the resistance of the section. We did one example yesterday where we knew the strength of the concrete, we knew the dimensions, we subtracted the area of steel from the concrete dimensions, and we multiplied the steel side by its stress, and we got NU's, the permissible force that we can carry. All right, N balance, 0.25 FCU BD, right? So I'm not going to go into detail of where that comes from, just take it for now as is. Or if K is greater than 1 from above, so if you calculate K and it comes out, what is N? N is the actual value of the load, okay? So if K is greater than 1 from above, then K is equal to MI over M balance. MI is 0.4 M1 plus 0.6 M2, okay? And but not greater than 0.4 M2. And this comes out from the deflection stories and the equations that are shown to you on page 6.1.2. Okay, so it comes up from there, right? When it's taking into consideration all those sketches that you have on the left-hand side. Right, we don't have the time to go in through its derivation for now. M balance 0.87 FY ASC, again, known or unknown, D minus D dash over 2, and then 0.646 FCU BD squared, right? So that is M balance, that's MI, you plug in your values, and it's done. The problem is we're starting with an unknown area of steel, so that's where our headache is. All right, so what we actually have to do is make an assumption and then redo the calculation and see where we're coming out with K. That's what happens. And then we may have to iterate this a couple of times till we get to the right answer. All right, so you have axial load and you have bending moment, and N and M balances there. Capacity when the moment is, when the force is 0 and it's only more bending moment, so it's behaving like a beam. So this is the beam part of it. Whoops, sorry. Right, so this is the part that gives you the behavior as a beam. This is the part that behaves as a column, pure column, without any moment. So that's axial, and this is bending. And then because you're combining the two, you get an effect. And you actually end up with, depending on whether you are bending in both directions or single direction, okay, you'll end up with one curve or a three-dimensional curve. Okay, so you can refer to the text on that and you'll see that it looks something like this, because now you've got it in 3-dimension. Okay, so it's sort of put it like that now. 3D, I'm trying to draw 3D and I'm not. So something like that. Okay, so that's 90 degrees at the base. So you'll get one curve about that axis. You'll get another curve about that axis. And then you are somewhere in between here. Okay, so you're picking up on a curve there somewhere. You follow what I'm saying? All right, so this is what happens when you do it in 3D. So this is in a single plane. It's a bit more complex when you look at it as a 3-dimensional model. Okay, so let's go then to, we discussed this already. Right, next step then, what is the next step in the design procedure? If it is slender, calculate additional moment, K, AU, M additional, okay? And as I said, if you don't know the steel area, this is K becomes, you just plug in 1 and you see what happens, then you see, put it back and you see what it should be and you play with it like that. Brace slender columns. If you've just got pinned at both ends, the M additional is just going to be in the center. Okay, if you've got a braced slender column, all right, so it's braced, it's not going anywhere, but you got fixity at one end. So you know from moment distribution that you got a moment in the middle, the moment at the end is going to be like half the value. Well, not from here, but what I'm saying to you is we're saying that the effect in the middle, you're going to get half the effect at the ends, right? So for example, now if you got it fixed top and bottom, you're going to get M add top and M add bottom. You then look at your possible bending moment diagrams for a fixed one. It's going to look like this, something like this, M1, M2, and you got M2. So look at which side it's coming on. This side has got tension on that side. This has got tension on this side. All right, so your diagram is doing this. Tension, tension on that face. Are you with me? So this one is in compression there. Okay, so you've got T minus C. So you've got M2, the original one, which was that. And then you got it on the other side, you got M add divided by 2. So this is why this one is looking smaller. All right, it's M2 minus M add divided by 2. If you look at these ones, they're on the same side, so it gets added up. All right, Mi plus M add. So you got the faint lines, the original one, and then the final. And on this side, again, you can see tension is on the same side. So you're going to add that one and that one up, and you get Mi plus M add over 2. All right, so that's basically what happens there. And then they, for an unbraced one, slender column, all right, your M additional just goes out, because remember now the frame can sway. In the previous one, there was no sway. So here you had frame fixed, but you had bracing across, right? Okay, So put this picture on in the book where you've got it so you understand it. And when it's unbraced, now you know from sway structures, that's unbraced, so you're expecting qualitative deflected shape one way or the other to look like that. Sorry. To look like that, I should have used another color there for the deflected shape. So it's going to deflect like that and deflect like that. And of course, what I'm trying to show you is that all the deflection is on one side. All right, so that's your, if you look only at the sway, you can see that your bending moment's on the outside and that you're adding, so M on the top gets added up and M1 at the bottom is reduced in proportion to the ratio of the end stiffness. Okay, all right, so there's a difference between unbraced and braced slender columns. And you see the ratio of the end stiffness becomes critical. Okay, is it 100% fixed, partially fixed, etc., etc., etc. Okay, you don't have to work all this out. You've got equations that do this for you. All right, if it is short, define the axis moment. If it is slender, calculate the additional moment. So that's the way you proceed, right? And the next design moment, the design moment about the either axis should not be less than the minimum. We did this yesterday. It's taking the actual load, multiplying it by E minimum. E minimum is 0.05 times the depth. And this is to cater for imperfections in the column or misalignment on the column beam, etc. This minimum eccentricity should not, however, be taken to exceed 20. So you got 0.05 times E, 0.05 times the dimension, but it mustn't be taken as exceeding 20, right? The moment thus obtained we used to calculate the reinforcement in the column, and we refer to the design moment. And then what's happened here is they put braced columns. These are the options. M2 or M1 plus, add brace slender. Where's brace slender? There we have it here. Brace slender. So the options that you've got, you can see this one became smaller, right? So we don't concern ourselves with the top. We concern ourselves with that. Sorry, I'm using another color there. We're concerning ourselves with that one and that one because this became greater, that became greater, but this one became less. So no drama there. It's pretty straightforward. M2 or M1 plus M add over 2 MI. Second case, MI plus M add. So it's possible that MI plus M add is more critical, or it's possible that E minimum times N, which is obviously usually just a check that you're not going below the minimum moment. All right. So unbraced slender columns, only two options. This one increases, this one reduces. So you take the increased one, and the increased one is going to be M2 plus M add. And always you're checking it against E minimum N. So M2 plus M add gives you 50 kilonewton meters, but E minimum times N gives you 60 kilonewton meters. You're going to use a 60 instead of the 50. That's also, it's just a check that you're greater than NE minimum. Okay, short columns, there's no braced or unbraced. There's no additional moment because it's short. It fails by crushing. Okay, these two, you have a combination of buckling and crushing. So for braced slender and for unbraced slender column, you take into account the buckling plus the crushing. But when it comes to short columns, there's nothing there to add on to it. Okay. Design procedure, we now have to design for the moments MX and or MY. So you've got two situations. You've got a moment in one axis or you've got a moment in two axis. So what happens? Uniaxial, I did one with you yesterday. Pretty straightforward. You just take that particular moment and you calculate its the information that you need to enter the graph, and you're gone. So one check, E minimum. We did the example yesterday afternoon with the moment in one direction. Okay, the column was designed to. So here we're looking at in columns that are bent about both axes. Okay, we don't design it because of that diagram that I showed you earlier, interacting between the two curves. So you got that 3D image, which is difficult to solve. So what they do is they calculate they increase the moment in one direction because of the other. What do we do in steel? What do we do in steel? Combined bending and compression. Any idea? You did steel design and concrete design last semester introduction, but maybe you didn't cover combined bending and compression. So there you have it more like the structural analysis type of stuff, P upon A plus M upon Z in the X plus M upon My over Z. So Zx, Zy. So you got it in that form. You got an interaction in steel. Steel is a lot nicer and easier to deal with. The relationship between the theory and the design, you can see it in the design formula, right? It's not in that form exactly, and it's in a slightly different form, but for now, I just want to emphasize the, what do we call it? Sorry. I don't want to get into the stuff that is added onto this. There's a U1X and a U1Y, etc. But I don't want to get into all of that. Second semester, when you're doing steel design, you'll come into it. All I want to say is it's a lot simpler in steel than it is in concrete. Concrete's using deemed to satisfy conditions. You don't actually deal with the stress in each direction, just like deflection. Deflection was a deemed to satisfy. Use table 10, table 11, and a T factor, and if it works, you don't do the detailed calculation. Right, so similar thing with this. Okay, right, so what do we do next is we into the design moment, right? And we look at mx over h or my over b, and which one has got the greatest ratio, and we'll see it in an example. Okay, calculate the enhanced moment for the design axis, and then these two equations apply. So if it's about the mx axis, you've got to increase the my one. And if it is about the my axis, you're increasing the mxy. So this is how the code handles it. It links it. So this thing links it to mx, and that links it to my. So you're looking at as though you've changed the biaxial bending into a uniaxial bending in terms of the graph. All right. And then there's a handy table 21, which just tells you that if you've got n upon BH FCU, then beta B is going to be this number. So pretty straight. We'll go into an example just now. Okay, we now have the final design values of n and m. And once we got that, we need to find d prime, not d prime. Okay, and d prime depends on the on the axis in each direction. Usually we go for the same cover, the same bar diameter, so it's usually the same. But anyway, you can see that the ratio will change drastically with the dimension of the beam. Okay, so that's the next thing. Once you've done that, select a design chart and read off the required rebar. I will show you also one design chart, which is independent of the grade of concrete. Now I just need to remember where it was. I think it is in H. Allen or it is in Reynolds. Somewhere I'll find it and I'll show you what it looks like. So you can use that graph when you've got a grade of concrete which is different. Like Greg's done it for 30 MPa. You have 25 MPa, you have 35 MPa, you're going to have a different graph. In the old codes, they had the whole variation of graphs which were attached to the annexure. There isn't one like that now. You basically got to pick up the graph. Now, because of computers, they said you can do it yourself. Okay, so this is what a graph looks like. It has the strength of the concrete. It's restricted to that. The yield strength of the steel. This is D prime over H. D prime is the dimension from the face to the nearest steel, okay, and center. So that assumes something like 0.2. And then you've got n upon bh squared, m upon bh squared, and you go n upon bh and m upon bh squared, and you get to the value. Then this is what we were doing yesterday. We took a ruler Okay, and we put it in here, for example, and we said, well, I think you can see it now between those two red lines. I have something like what? 8. And this is like 4, so it's halfway. You follow what I'm saying? So you can play with it. You can turn the ruler in that direction and say, well, that's better. It looks like 5 between the two of them. And this one is like 2.5. Yeah, so it's halfway. Are you with me? So you can use a ruler like this. You can use a ruler at any angle, that just to make it convenient to read a scale. That's all. Okay, and you pick it up. Any questions so far? So that's the theory behind it. And once you've got that, you take into account all the other considerations, which are at least 1 bar in each corner, at least 6 in circular columns, 0.4% of gross cross-sectional minimum. Minimum bar size is 12. Okay, then you have no more than 6% maximum, no more than 8%. Okay, no more than 10%. Usually we have vertically cast, so horizontally cast not too common. Okay, then other considerations is detailing, and longitudinal bars need to be placed about the x-axis. Okay, please be careful. So you got a moment about the x-axis, so it must be placed about that direction. This is biaxial. Remember, you had a moment in both directions. That's why you got it like that. But if you had a moment only about the x, right, you had a moment only about the x-axis, then your steel must be like this. Are you with me? All right, so no steel on the center line then. So uniaxial, no steel on the center line. Biaxial, have it both directions. Okay, so that covers the theory. Do you have any questions? Do you have any questions? Okay, what are these lines that you see on the graph? Greg has shown some of them, not all of them, but what are they? These, you'll see on a graph, you have these dotted red lines. Okay, see that line? That line, that line, there's a whole lot more. Okay, and here I will refer you to Vernon and Marshall, page what is this? 11,8. Right, so this deals with those kind of issues like x over h. So here you're talking about x over h. All right, it's these there's lines that you can plot on. There's a line here which represents E minimum, and it's usually where there's a change in the curve. So you would get E is equal to 0.058. So at that point, that's where you get that happening. Are you with me? And then the others are representative of the X. So you could put in various. So what you have is being able to flex the depth of the zone in compression, right? Okay, so X is the depth in compression, if you like. Okay, so based on that, you are able to play with your reinforcement. You can manipulate it. Okay, but for our purposes, as I said, you can read it in the commentary part of Vernon and Marshall. It's chapter 11, the first few pages, page 1 to page 12. So chapter 11, 1 to 12. You'll find it in all the textbooks. You'll find it in Mosley and Bunge. You'll find it in all of those books that are in the library. Okay, so you'll find the description for it there. Reynolds, all of those. Okay, so that's basically where we are in terms of the theory behind the design. What we're going to do now is going to move on to the example. So we come back to the example, and the second part of the example was finding the additional moments. So example, where are we? Sorry. Where is example 6.2? I had it somewhere, I don't know. There's a whole lot of theory in the book, but difficult to follow if you're not given all the appropriate diagrams. But example 6.3 covers now everything, including the detailing. I'm just looking for example 6.2. Give me a second. Where's example 6.2? Example 6.2 is on page 6.16, 6.17. All right, so I just want to stop here, give you a 10-minute break, look through the book, get familiar with where things are, make a note of them, write them down. Okay, it's not a difficult section at all columns. I can make it more difficult by asking you to calculate the moments using moment distribution. So this is given, and I can add to the problem by saying, okay, now work out the moment at the top and the bottom of the column using moment distribution, using the analysis of frames, which I discussed right in the beginning. So that's where I can throw some challenges in to otherwise, what would otherwise be a very boring design. So what I'm saying to you, it's more realistic. All right, but my aim and my function is to get you into the design of the column, and you've picked up the load and you've picked up the moments from a computer analysis, and you're now designing it. All right, so let's say we discuss the other issues at another time. We just talk about this one for now, okay, without the analysis being thrown into it. I'm scared because I marked 12 scripts so far. I was naughty. I took the ones that normally get 100% first, had a look at those, and then I looked at the others, and I can see where the shortfalls are. But what I'm doing is I'm making it, and you're asking me why I'm only marked 12 scripts. Putting a mark is easy. Checking the GA and me writing down next to it where the student has fallen short. So that's where I have to have an interview with the student, right? And get to understand whether he knows what's going on, then he doesn't write the supplementary. But if a student clearly under 50 will write the supplementary irrespective, okay? All right. Any questions? So just a small break here, guys. Any questions? Any questions so far? You're just exhausted from the transport test this morning. Huh? Oh, very, very quiet. Shame. Must have taken its toll on you this morning. How many people do I have? The rest are fast asleep, catching up sleep that was lost last night. Not my problem. I've got a class to deal with. Okay, so I'm just going to stop here temporarily and we'll continue. So give you a small break, get a nice something to wake you up, whatever. Right.